In this video, I will talk about metric measurement scale, and this is the part third video about an overview of multivariates method. Let's first we'll talk metric measurement scales. In contrast to non-metric data, metric data are used when subject different in amount or degree on a particular attribute. Metrically, measurement variables reflect relative quantity or degree and appropriate for attribute involving amount of magnitude, such as the level of satisfaction or commitment to a job. The two different metrics measurement scale are interval and ratio scale. First, what is the interval scale? Interval scale and ratio scale, both metrics provide the highest level of measurement precision, permitting nearly any mathematical operation to be performed. These two scale has constant unit of measurement. So difference between any two adjacent point of any part of the scale are equal. In the preceding example, in measuring satisfaction, metric data could be obtained by measurement the distance from one end of the scale to each product position. Assume that product A was 2.5 units from the left end, product B was 6.0 units, and product C was 12 units. Using this value as the measurement of the satisfaction, we could not only make the same statements as we made with the ordinal data. For example, the rank order of the products. But we could also see that the differences between the product A and product B was the similar 6.0 minus 2.5 is equal to 3.5. Then was the differences between the product B and C 12.0 minus 6.0 is equal to 6.0. Then only real differences between the interval and the ratio scales is that interval scale used an attribute arbitrary 0 point, whereas ratio scale include an absolute 0 point. The most familiar interval scale are the Fahrenheit and the Celsius temperature scales. Each use of different arbitrary 0 point, and neither indicate a zero amount of lack of temperature, because we can register temperature below the 0 point on each scale. Therefore, it is not possible to say that any value on any interval scale is a multiple of some other point of the scale. For example, an 80 degrees Celsius F day cannot correctly be said to be twice as hot as 40 degrees Celsius day, because we know that 80 degrees Celsius and the different scale each as Celsius is 26.7 degree C Celsius. Similarly, 40 degree F on the Celsius scale is 4.4 Celsius. Although 80 degree is indeed twice 40 degree, one cannot state that the heat of 80 degree is twice the heat of the 40 degree, because using the different scale, the heat is not twice and great, that is 4.4 degree Celsius into the 2 and 26.7 degrees Celsius. Let's talk about the ratio scales. Ratio scale represent the highest form of measurement precision, because they possess the advantage of all over the scale plus an absolute 0 point. All mathematical apportations are permissible with ratio scale measurement. The bathroom scale of the other common weighting machines are example of these scales, because they have an absolute 0 point, and spoken of the term of multiple when rating one point on the scale to another. For example, 100 pound is the twice as heavy as the 50 pounds. The impact of the choice of measurement scale. Understanding the different type of measurement scale is important for two reasons. Number one, the researcher must identify the measurement scale of each variable used, so that non-metric data are not incorrectly used as the metric data, and vice versa. As in our earlier example of repre- rep- representing gender as 1 for male and 2 for female. If the research incorrectly defined this measurement as matrix, then it may be used inappropriately, for example, finding the mean value of the gender. The measurement scale is also critical in determining which multivariate techniques are the most applicable to the data, with considerations made for both independent and dependent variables. In this discussion of the technology and their classification in later section of this chapter, the metric or non-metric properties of independent and dependent variable are the determining the factor is selecting the appropriate technique. Measurement error and multivariate measurement. This use of the multiple variable and the reliance of their combination, the variate. The multivariate techniques also focus attention on a complementary issues, measurement error. Measurement errors is the degree to which the observed data are not representative of the true values. Error is the degree to which the observed value are not representative of the true values. Measurement as many sources ranging from the data entry across to the impressions of the measurement, imposing 7-point rating scale for attitude measurement when the researcher known the userment and the respondent can accurately respond only to a 3-point rating to the ability of the respondent to accurately provide information. For example, responses as to household income may be reasonable, accurate, but totally precise. Those all variables used in multivariate technique must be assumed to have some degree of measurement error. The measurement errors add noise to the observed or measured variable. Those the observed value obtained represent both the true level of the noise. When used to compute correlation or means, the true effect is partially marked by the measurement error, causing the correlation to weaken at the means of less precise. Validity and reliability. The researcher's goals of reducing measurement error can follow several paths. In assessing the degree of measurement error precise in many measures, the researcher must address two important characteristics of the measurement. First, validity. What is this? This is the degree to which a measurement accurately represents what is the supposed for. For example, if we want to measure discriminatory income, we should not ask about total household income. Ensuring validity start with through the understanding of what is to be measured and then making the measurement arc as correct and accurate as possible. However, accuracy does not ensure validity. In our income example, the researcher could precise define total household income, but it should still be wrong. That is the invalid measurement. In measuring this certainty income because the correct questions was not being asked. If validity is assured, the researcher must still consider the reliability of the measurement. Reliability is the degree to which the observed variable measures the true value and is error free. Thus, it is opposite of the measurement error. If the same measurement is asked repeatedly, for example, more reliable measurement will show greater consistency than less reliable measurement. The researcher should always assess the variables being used and if valid alternative measurements are available, choose in variable with the higher reliability. Let's talk about the employing multivariate measurement. In addition to including measurement error by improving individual variables, the researcher may also choose to develop multivariate techniques, also known as summit scale, for which several variables are joined and composite measurement to represent the concept. For example, multiple item personality scale or summate rating scale or product satisfaction. The subject is to avoid the use of only a single variable to represent a concept and instead to use several variables and indicators, all representing different factor of the concept to the obtain or more well-rounded perspective. This use of multiple indicators enable to research to more precise specify the desired respondents. It does not replace total reliance on the single responses but instead on the average or typical responses to set of the related responses. For example, in measuring satisfaction, one could ask a single question, how satisfied are you? And base the analysis of on the single responses, or a summate scale could be developed that combines several responses of the satisfaction. Finding the average score among the three measurement overall satisfaction, the likelihood to recommended and the probability of the purchasing against the different measurement may be different responses for of the different areas of interest assumed to com, com, comprise overall satisfaction. The guideline premises is that multiple responses reflect the true responses more accurately than does a single response. The researcher should assess reliability and incorporate scale into the analysis. The impact of measurement error. The impact of measurement error and poor reliability cannot be directly seen because they are embedded in the observed variable. The researcher must therefore always work to increase reliability and the validity, which in turn will result is a more accurate portrayal of the variables of interest. Poor results are not always due to measurement error, but the presence of the measurement error is guaranteed to distort of the observed relationship and make multivariate techniques less powerful. Reducing measurement error, although its takes make multivariate technique less powerful. Reducing measurement error, although its take efforts, time and additional resources, may improve weak and margin result and strengthen proven as well as. Let's talk about the statistical significance versus statistical power. All the multivariate technique except for the cluster analysis and perpetual mapping are based on the statistical interface of the population values or relationship among variables from the randomly drawn sample of the population. Assumptions of the entire population make statistically interface unnecessary because any differences or relationship, however small, is true and does exist. Researchers very seldom use to sanctions. Therefore, researchers are often interested in a drawing interface from a sample. Type of the statistical error and statistical power. In statistical error, there are alpha A error, we call it type 1, and beta error, we call it type 2. Let's talk about that. Interpreting statistical interface required the researcher to specify the acceptable level of the statistical error that result from using a sample known as sampling error. The most common approach is to specify the level of type 1 error and also as alpha A. Type 1 error is the probability of the rejecting the null hypothesis when it is actually true, generally referred to as false positive. By specifying as alpha level, the researcher set the acceptable limit for error and indicate the probability of the conducting the significance exists when it really does not. When specifying the level of type 1 error, the researcher also determined an associated error term type 2 error. We call it beta error. The type 2 error is the probability of not rejecting the null hypothesis when it is actually false, and extension of the type second error is 1 minus beta, referred to as the power of the statistical interface test. Power is the probability of the correctly rejecting the null hypothesis when it should be rejected. Those power is the probability that statistical significance will not indicate it is present. The relationship of the differences error probabilities and the sitting for the differences in the two means is shown here. Here's the statistical decision H0, the hypothesis no differences. We call it 1 minus A, no differences, and differences beta second error. H8 differences A error, the beta 1 minus B power. Although specifying alpha established a level of acceptable statistical significance, it is the level of the power that indicate the probability of the success in finding the differences if they actually exist. Why not set alpha and beta at acceptable level? Because the type of 1 and 2 error are inversely related. Those are type 1 error become more restrictive, more closer to 0 as the probability of the type second error increase. That is, reducing the type 1 error reduce the power of the statistical test. The researcher must strike a balance between the level of alpha and the resulting power. Let's talk about the impacts on the statistical power. But why? Why can't high level of the power always be achieved? Power is not solely a function of alpha. Power is determined by the three factors. Number one, effect size. The probability of achieving statistical significance is based on not only the statistical correlation but also the actual size of the effect. Those effect size help to researcher determine whether the observed relationship differences or the correlation is meaningful. For example, the effect size could be differences in the mean between the group or the correlation between the variable. If a weight loss from claim is program leads to an average weight loss of 25 pounds, the 25 pounds is the effect size. Similarly, if a universe claim its MBA graduate get a starting salary that is 50% higher than the average, the percent is the effect size attributed to earning the degree. When examining the effect size, a larger effect is more likely to be found than a smaller effect and is the more likely to impact the power of the statistical test. To assess the power of statistical test, the researcher must first understand the effect being examined. Effect sizes are defined in a standardized term from ease of comparison means differences are stated in terms of the standard deviation. Those an effect size of 0.5 indicate that the mean differences is one of half of the standard deviation. For correlation, the effect size is based on the actual correlation between the variables. Alpha A become more realistic, power decrease. Therefore, as the researcher reduce the chance of the correctly saying an effect is a significant when it is not a probability of correcting finding and affecting decrease. Conventional guidelines suggest alpha level of 0.5 or 0.01. Researchers should consider the impact of particularly alpha level on the power before the selecting the alpha level. The relationship of these two probability is illustrated in later discussion. Let's talk about the sample size. At any given alpha level, increased sample size always produce greater power for the statistical test. As sample size increase, researcher must decide if the power is too high by too high. We means that by increasingly sample size, smaller and smaller effect, for example, correlation with the found to be statistically significant until at the very last sample, almost may effect is a significant. The researcher must always be aware that sample size can affect the statistical test either by making it sensitive at a small size over a sensitive a very large sample size. Let's talk about the relationship among the alpha sample size, effect size, and power of the complicated, but a number of the sources are available for consideration. Coherence examine power of the most statistical interface test and provide guidelines for acceptable level of power, suggesting the studies be designed to achieve alpha level of the latest 0.05, the power level of 80% to achieve such power levels. All three factors alpha sample size, effect size must be considered simultaneously. These intercorrelationship can be illustrated by the sample example. The example involved testing for the differences between the mean sources of two groups. Assume that the effect size is though to reduce between the small and the moderate. The researcher must now determine the necessary alpha level and the sample size of each group. Table 1 illustrates the impact of both sample size and alpha level of the power. Note that with the moderate effect, the power reach alpha one level at the sample size 100 or more than alpha, even the more flexible alpha level of the sample size of 200 or more. For example, if the effect size is a small sample size of 200 with an alpha of 0.04.5, still has only a 50% of chance of significant differences being found. This suggests that if the researcher expects that the effect size will be small, the study must have larger sample size or restrictive alpha level, suppose 10. Here is the table 1 power level of the comparison of two means variation by sample size, significance level of effect size, alpha a 0.05 and alpha 0.1 effect size. These are the sample: small, moderate, small and moderate size. Next video I will talk about the using power with the multivariates technique.